This video focuses on a fundamental concept in physics, one that remains enigmatic. This phenomenon influences a wide range of occurrences, from molecular collisions to formidable storms, the inception, evolution, and ultimate fate of the universe. It might even influence the arrow of time and underlie the existence of life itself. To comprehend its perplexing nature, we can begin by posing a simple query. What does the sun contribute to the Earth? Indeed, on a daily basis, the Earth receives a certain amount of energy from the sun. How much energy, in comparison, does our planet emit into space? For much of its history, the Earth has likely radiated the same quantity of energy into space as it has absorbed from the sun. Were this not the case, our planet would be experiencing much more intense heating, an uncomfortable scenario. Assuming this is the norm, then what exactly does the sun provide us? The sun offers something exceptional. To uncover the solution, we must recall a discovery from 2 centuries ago. In the winter of 1813, the forces of Austria, Prussia, and Russia entered France. On December 29, Sadi Carnot, the 17-year-old son of a general, sent a letter to Napoleon requesting to join the battle. Napoleon, engrossed in warfare, didn't respond. Yet this wish was fulfilled several months later. Hostilities erupted in Paris. Students, including the general's son, stood in defense of the estate to the east of the capital. Nonetheless, they proved powerless against the invading army, resulting in Paris falling within a day. This forced withdrawal plunged Carnot into despair. 7 years afterward, he visited his father, who had sought refuge in Prussia following Napoleon's downfall. The senior Carnot not only served as a general, but also delved into physics. He composed an essay on the efficient transfer of energy in mechanical systems. When his son arrived in Prussia, they engaged in extensive discussions about the groundbreaking innovation of that era, the steam engine. This invention had already found practical applications in various sectors such as shipping and ore mining. It was becoming evident that a nation's industrial and military prowess would soon be determined by the quality of its steam engines. France was trailing behind countries like Britain and others in this domain. Sadi Carnot took it upon himself to uncover the reasons behind this disparity. During that period, even the most advanced steam engines could only convert around 3% of heat energy into useful work. By enhancing this efficiency, Carnot believed he could grant France a significant advantage and help it reclaim its former global standing. He dedicated the following 3 years to the study of heat engines. One of Carnot's notable accomplishments was the creation of a theoretical model for an ideal heat engine, devoid of friction and energy loss. Here's how this concept operated. This setup involved 2 oversized metal bars, referred to as the heater and cooler. The engine itself comprised an air-filled chamber with limited heat exchange through the bottom. Inside this chamber was a piston connected to a flywheel. The air within the cylinder needed to be heated just slightly below the temperature of the hot bar, onto which the apparatus was positioned. As the warm air expanded, it set the flywheel in motion. Simultaneously, due to the continuous heat influx from the heater, the air's temperature remained constant. By removing the heater, the influx of heat into the chamber ceases. However, the heated air continues to expand for a certain duration. Ideally, this expansion persists until the air's temperature declines to match that of the refrigerator. Subsequently, the cylinder is placed on the cold bar, causing the flywheel to propel the piston downward. This action compresses the air, leading to the dissipation of heat into the colder metal. Upon removing the cooler, the flywheel's motion persists, further compressing the air, which is now heated to just below the temperature of the heater. The process is completed by returning the hot bar. This cycle repeats, effectively converting the heat from the heated metal into flywheel energy. Intriguingly, the ideal Carnot engine can be operated in reverse. When the cycle is reversed, the air initially expands, resulting in a temperature decrease. Placing the piston on the cold bar causes the air to continue expanding, absorbing heat from the metal and subsequently compressing, causing the temperature to rise. Upon positioning the chamber on the hot bar and utilizing the flywheel's energy, the heat is redirected back to the heater, regardless of the number of cycles executed in one direction. An equal number of cycles can be repeated in the opposite direction. Ultimately, all components return to their original states, necessitating no additional energy within the system. In essence, when this ideal engine is operational, no actual change takes place. Every action performed can be reversed. However, what level of effectiveness can be attributed to such an engine if its functioning is fully reversible? One might be inclined to assume a perfect score of 100%, but alas, this is not the case. In each cycle, the flywheel accrues energy from the heat introduced into the chamber alongside the air. This heat is absorbed as the metal becomes hot and then diminished as the cold bar comes into contact, extracting heat. To determine the efficiency, one must divide this energy by the heat provided by the heater. The heat input from the hot side corresponds to the work exerted by the gas as it propels the piston outward. This work will consistently surpass the effort of the piston as it compresses the air above, equivalent to the heat released at the outlet. Invariably, a heated gas exerts greater pressure on the piston compared to the same gas at a colder state. To enhance the engine's efficiency, there are two primary avenues: either elevating the heater's temperature or reducing the cooler's temperature, or a combination of both. Upon grasping the concept of the ideal heat engine, Lord Kelvin recognized the feasibility of devising a temperature scale grounded in it. Envision a scenario in which, under specific conditions, a gas undergoes expansive growth to such a degree that its temperature decreases to a point where its particles effectively come to a standstill. Consequently, they no longer apply pressure on the piston, rendering compression against a cold bar effortless. In this scenario, no heat is lost. This theoretical state is what we refer to as absolute zero. Under these circumstances, the engine's efficiency would reach 100%. By utilizing the absolute temperature scale, the Kelvin scale, we can substitute the quantities of heat entering and exiting with the temperatures of the heated and cooled sections respectively, as they are directly proportional. Thus, the output can be expressed in this manner, which subsequently transforms into the following representation. In summary, this presents an intermediary conclusion. The efficiency of an ideal heat engine is contingent not upon specific materials or a particular design, but rather on the temperatures within the heater and cooler components. To attain a perfect efficiency of 100%, one would necessitate an infinitely elevated heating temperature or the attainment of absolute zero for cooling. Regrettably, neither of these extremes can be practically achieved. This implies that even in a scenario devoid of friction and leakage, realizing a heat engine with 100% efficiency remains unattainable. This is due to the requirement of transferring heat to the cold bar in order to restore the piston to its initial position. Consequently, not all of the energy becomes stored within the flywheel. During Carnot's era, high-pressure steam engines never exceeded temperatures of 160 degrees Celsius. Theoretically, their maximum attainable efficiency was 32%, while practical implementation likely yielded around 3%. The underlying reason lies in the presence of friction in actual engines, resulting in the dissipation of heat into the surrounding environment, coupled with uneven temperature transfer. Consequently, less energy is directed to the flywheel than the amount of heat supplied, with a significant portion being absorbed by the cylinder walls, funneling into the flywheel axis, and ultimately dissipating into the surroundings. This mode of energy dissipation precludes the possibility of reassembly, rendering the entire process irreversible, while the total energy quantity remains constant. Harnessing it for useful work becomes considerably more challenging. Utilizing concentrated energy proves more convenient than dealing with energy dispersed throughout space. Several decades later, Rudolf Clausius, a German physicist who had extensively studied Carnot's ideas, developed a method to quantify the extent of energy dispersal. He termed this measure of dispersal entropy. When all the energy is concentrated within a hot source, entropy remains low. However, as energy diffuses into the surroundings, raising the temperature of the chamber walls and the axis, entropy increases. Essentially, the total energy remains constant, but in its dispersed state. It becomes more challenging to harness for practical work. In 1865, Clausius articulated the first two laws of thermodynamics in the following manner. The first law asserts that the total energy in the universe remains constant, while the second law states that entropy in the universe tends to rise, signifying a progression towards energy dissipation. In simpler terms, energy disperses over time. This second law underpins numerous natural phenomena. Hot substances cool, cold substances warm up, and gases fill available space. Moreover, it renders perpetual motion an impossibility, as the quantity of usable energy in a closed system incessantly diminishes. Commonly, entropy is perceived as a measure of disorder, a concept that intuitively aligns with the breakdown of an organized structure. Nonetheless, it is more accurate to conceptualize entropy as the propensity of energy to scatter. Yet, why does this phenomenon occur? Much of the fundamental principles in physics operate symmetrically in both forward and backward time directions. So why does energy inevitably disperse as time progresses? Consider two small metal bars, one hot and one cold. Let's simplify the model significantly. Each bar consists of only 8 atoms, and the vibration of these atoms corresponds to a specific quantity of energy units. The magnitude of these vibrations depends on the number of energy units present. More units lead to more pronounced vibrations. For our initial scenario, let's imagine the left bar containing 7 energy units, while the right bar holds 3. This configuration of energy in the bars can be referred to as a state. Initially, we'll focus on the left bar. This bar contains 7 energy units that are free to move among the lattice of atoms. These units randomly jump between atoms, causing a reshuffling of energy distribution. However, the total amount of energy remains constant throughout these exchanges. Now, let's turn our attention to the cold bar, which possesses a lower amount of energy. Placing the bars on top of each other enables energy units to move between atoms in both bars, leading to the formation of various configurations. All distinct combinations are equally likely. Imagine taking a snapshot at a specific moment in time to assess the distribution of energy units. And stop. Upon analysis, we observe that there are now 9 energy units in the left bar and only 1 in the right bar. It appears that heat has moved from the cold bar to the hot bar. This might seem puzzling since this movement would suggest a decrease in entropy. At this juncture, it's pertinent to recall the insights of Ludwig Boltzmann. While transferring heat from a colder to a hotter object is technically feasible, it's highly improbable. To put it simply, it's an unlikely occurrence. In this context, there exist a total of 91,520 combinations where the left bar holds 9 energy units, compared to 627,264 combinations with 5 units each. Indeed, when we consider an equal distribution of energy between the two bars, such a state becomes approximately 6 times more likely. If we account for all possible combinations, the outcome suggests that there is a 10.5% chance of more energy units accumulating in the left bar compared to the initial arrangement. However, this raises a question. Why don't we actually observe such occurrences? To address this, let's examine a scenario where we increase the number of atoms in the bars to 80 and amplify the energy units to 100. This time, there are 70 units of energy in the left bar and 30 in the right. Surprisingly, the likelihood of the left bar becoming hotter than its initial state is only 0.5%. Furthermore, this probability diminishes even further as we continue to augment the number of atoms. In reality, solid materials consist of billions of trillions of atoms, accompanied by an exponentially larger number of energy units. The probability of heat transferring from a colder object to a hotter one becomes so minuscule that it virtually never occurs. A similar analogy can be drawn using a Rubik's Cube. Envision a fully assembled cube, and then shut your eyes and start disassembling it. As you manipulate the cube, it progressively deviates from its original ordered state. How can you be sure that you're dismantling it rather than the reverse? The reality is, when fully assembled, there's just one possibility. As it nears completion, there are multiple options and countless combinations that turn out to be essentially random. Without intentional effort, Each twist steers the cube further from the improbable, the assembled state, and closer to the probable, chaotic state. But considering that energy and its surroundings typically tend toward disorder, how can we explain the functioning of air conditioners? They, after all, cool rooms that are already cool while heating the warm air outside. Energy flows from cold to hot, decreasing the disorder within the house. However, this is achieved by increasing disorder more significantly elsewhere. In the case of air conditioners, this happens at a power plant, where stored chemical energy from coal is released, warming the plant itself, the turbines of electric generators, and even the cables transporting electricity to households. Fans and compressors in the air conditioners then eliminate the excess heat. The reduction in disorder within the house is outweighed by the heightened disorder during the electricity generation process. But if the overall disorder in the universe is constantly on the rise, and our actions merely contribute to its increase, why is there any order on Earth? How come we have extremes like scorching hot and freezing cold? Why does life thrive? If our planet were a closed system, energy would indeed dissipate, life would vanish, and everything would degrade and merge. Sooner or later, temperature equalization would occur. However, fortunately, that's not the scenario we find ourselves in. This is all thanks to the sun, which provides a continuous supply of low entropy, concentrated energy. The solution lies therein. The sun furnishes us with a consistent stream of concentrated energy, which is more useful than the energy it emits in the form of radiation. This energy is denser and more focused. Plants harness this energy through photosynthesis, enabling their growth and the production of sugars. Animals then consume these plants, utilizing the resultant energy to sustain their bodies and support their active lives. Certain animals acquire their energy by consuming other animals, continuing the cycle. At each successive stage, a fraction of the energy is dissipated. Eventually, all the energy derived from the sun transforms into heat, radiating from Earth back into space. Nonetheless, the total quantity remains unchanged. The rise in entropy can be assessed through the relative count of photons received by Earth from the sun and the photons emitted by Earth. For every solar photon reaching Earth, our planet emits 20 photons. Everything on Earth, the blossoms in the meadows, the trees in the forests, the wildlife on the savannas, the tempests and whirlwinds, and even humans engaged in their daily activities, converts high-energy solar photons into lower-energy photons, albeit in a greater quantity of 20. Were it not for a source of concentrated energy and a means of dissipating it, life on our planet would be untenable. Some have even posited that life itself emerges as a consequence of the second law of thermodynamics. If the universe is inclined toward maximizing entropy, then life serves as an effective catalyst for accelerating this process, given its proficiency in converting low entropy into high entropy. In a water layer near the ocean surface, for instance, the presence of cyanobacteria and organic matter leads to a surge in entropy by anywhere from 30 to 680%. Jeremy England took an even more audacious stance, suggesting that a consistent influx of concentrated energy encourages the formation of structures that disperse this energy. Consequently, as time progresses, increasingly proficient dissipative structures arise, including life. In his own words, he contends that if atoms are exposed to light for an extended period, the eventual emergence of a plant should not be astonishing. Therefore, life on Earth owes its existence to the low entropy supplied by the sun. However, the question arises, where does the sun acquire its low entropy? The answer lies in the broader universe. It is postulated that entropy within the universe escalates with time. Consequently, entropy was lower yesterday than today, even lower the day before, and so on, tracing back to the moment of the Big Bang. In the immediate aftermath of the Big Bang, entropy reached its nadir in the annals of the universe's history. This proposition is known as the past hypothesis. It doesn't offer an explanation, but rather assumes the sequence of events based on the universe's evolution. Yet, during its inception, the universe was immensely dense, hot, and nearly uniform. It resembled a heated matter concoction, exhibiting minimal discrepancies, barely 0.001% in temperature. Such a state implies an exceptionally low entropy. At this juncture, the influence of gravity enters the equation, causing matter to coalesce. Considering this, a uniform dispersion of matter becomes an exceedingly improbable condition. Consequently, entropy assumes a low value. Over the passage of time, as the universe underwent expansion and transformation, regions of matter became denser and began to coalesce. In this process, an immense quantity of potential energy was converted into kinetic energy, which, akin to the way flowing water propels turbines in generators, could also be harnessed. These conglomerates of matter collided with each other, leading to the release of a portion of their kinetic energy as heat. As useful energy diminished, entropy correspondingly increased. During this course, useful energy was expended, facilitating the formation of stars, planets, galaxies, and the emergence of life, thereby driving an augmentation in entropy. The universe commenced with an entropy level of roughly 10 to the power of 88 multiplied by Boltzmann's constant. Presently, the stars observable in the universe possess about 9.5 times 10 to the power of 80. When considering the cumulative entropy of interstellar and intergalactic space, the figure surges nearly tenfold. Nevertheless, this remains merely a fraction of the entropy prevailing shortly after the universe's inception. A substantial surplus of entropy exists in the form of neutrinos and photons from relic radiation. In 1972, Jacob Bekenstein introduced a new source of entropy: black holes. As per Bekenstein's concept, the entropy of a black hole ought to be directly proportional to the surface area it encloses. In essence, as a black hole increases in size, its entropy correspondingly magnifies. Esteemed physicists initially did not accord significant weight to this notion, and this skepticism was warranted. According to classical thermodynamics, if black holes possess entropy, they must possess a temperature, and if they possess a temperature, they must radiate energy. Consequently, they would not exhibit the true blackness conventionally associated with them. Stephen Hawking aimed to challenge Bekenstein's concept, but surprisingly found evidence supporting it, discovering the existence of radiation, termed Hawking radiation, emitted by black holes. This radiation possesses a measurable temperature. The core of the Milky Way's black hole, for instance, has a temperature of approximately a minuscule fraction of a Kelvin. Although this radiation is extremely faint and elusive, Hawking successfully demonstrated the presence of entropy in black holes, aligning with Bekenstein's hypothesis. He refined his assumptions and calculated the precise value of entropy. The supermassive black hole at our galaxy's center, for instance, holds an entropy roughly 10 to the power of 91, surpassing early moments of the observable universe by a factor of 1,000 and overshadowing the cumulative entropy of all other particles by a factor of 10. When combined, the aggregation of black holes yields an astounding value, 3 times 10 to the power of 104 of Boltzmann's constant. This underscores the initial low entropy conditions. All occurrences in the universe, from the configuration of planetary systems to galactic mergers, asteroid collisions, stellar demise, and the proliferation of life, have been made feasible due to the continuous rise of entropy. This progression follows a unidirectional course where entropy invariably escalates, creating a distinct contrast between the forward and backward trajectories of time. This irreversibility is engendered by entropy, leading to an eventual dissipation of energy until all intriguing events become exceedingly rare. The eventual occurrence of the universe's heat death is anticipated. This distant event, projected to unfold more than 10 to the power of 100 years from now, will transpire as the last black hole undergoes evaporation, causing the universe to reach its most probable state. At that point, irrespective of the scale considered, distinguishing the forward or backward progression of time will become inscrutable, leading to the complete disappearance of its directional nature. Entropy appears to hold a somewhat ominous connotation, seemingly guiding us toward a gloomy culmination of cosmic affairs. However, the fact that maximum entropy corresponds to the simplest arrangement doesn't imply that minimum entropy corresponds to the most intricate one. For instance, take tea and milk stored separately, a rather unremarkable scenario. Yet, once milk is poured into the tea, they blend, generating captivating and delicate patterns of motion. These patterns emerge fleetingly, swiftly dissipating until a uniform liquid remains. Both states, characterized by high and low entropy, exhibit relatively uncomplicated structures. The true essence of meaningful occurrences lies within the intermediate states between these extremes. Given that we find ourselves in such a juncture, let's relish the existence of comparatively low entropy while we have the opportunity.